I will now talk about a very special type, very important and special case of relations or type of relations that we call equivalence relations. And before I define it, let me remind you of three important properties of relations. Binary relations on the same set, on set A. The first is reflexivity, the second is symmetry, the third is transitivity. Again, a relation is reflexive if every element in A is in relation to itself. It is symmetric if whenever AB is in the relation, BA is in the relation. It is transitive if whenever AB and BC are in the relation, then AC is in the relation as well. Okay? Now, a relation that satisfies all three of them is called an equivalence relation. So one example of that, suppose I define the relation R over the set of all natural numbers, 0, 1, 2, 3, all the way. And I define the relation as AB, where A is equivalent to B mod 3. Again, when I take A and B, divide them by 3, I get the same remainder. Notice that this relation is reflexive. Okay, so if you look at every element, every number in N, A mod 3 equals to A, right? So if you take A and divide it by 3, the remainder is the same if you take A divided by 3. There's no difference, right? So for every A in N, therefore AA is in the relation for every A. In other words, it is reflexive. If we have A is equivalent to B mod 3, this implies that B is equivalent to A mod 3, right? Because again, this equality is symmetric, right? So if I take A and B and divide them by 3, I get the same remainder. It doesn't matter if I first divided A and then divided B, or B then A, right? So this means that if AB is in R, then BA is in R. This means the relation is symmetric. And the third one here is that if A is equivalent to B and B is equivalent to C mod 3, then for sure A is equivalent to C mod 3, right? Because if the remainder of A and B and C divided by 3 are the same. So the remainder of A and C, when they are divided by 3, are the same. Therefore, if AB is in R and BC is in R, then I get AC is in R. Therefore, this relation is transitive. Since the relation is reflexive, symmetric, and transitive, we say that this relation is an equivalence relation, okay? And when we have equivalence relation, we have the notion of equivalent elements, okay? So two elements are equivalent if they are related by that relation. So A and B are equivalent. If A, B is in this relation R, that is an equivalence relation. So if we go again back to this set of natural numbers and the same relation of equivalence mod 3 here. So I can say, for example, that 0 is equivalent to 3, 0 is equivalent to 90, 0 is equivalent to 300. Why? Because if you look at 0 and 3 and 90 and 300, all of them, when you divide them by 3, the remainder is 0. Or in other words, 03 is in R, 090 is in R, 0300 is in R. The same thing if I take, for example, 10 divided by 3, the remainder is 1. So it is equivalent to any number whose remainder when we divide by 3 is 1. So for example, it is equivalent to 91. 10 is equivalent to 301, and so on. And 2 is equivalent to any number that when you divide by 3, the remainder is 2. So it is equivalent to 302. 2 is equivalent to 602. 2 is equivalent to 598, and so on. Okay, 99, sorry. So this is what we mean by equivalent or equivalence of elements. Now, under an equivalence relation and this notion of equivalence between elements, we can group all the elements in the set A, or in this case, all the natural numbers that are equivalent to each other. Notice, because the relation is an equivalence relation, if A is equivalent to B, then B is equivalent to A. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. Okay, so we will not have any conflict. We cannot have sets of pairs that some of them are equivalent to each other and some of them are not. So if I now take so for example, I take an element like 0, and I say, let me create a set of elements, all of which are equivalent to 0. Okay, so I take 0, I say, give me the set that contains 0 and all the natural numbers that are equivalent to 0. What do you get from there? What we get is something we call the equivalence class of 0. So the equivalence class of 0 are all the numbers that are equivalent to 0 under this relation. So under this relation, so this is the notation, if I take 0 and use this square brackets around it, I'm saying, what is the equivalence class of 0? It is 0 and all the numbers that are equivalent to it. So it's 0 and 3 and 6 and 9 and so on. In other words, this is the set of all the numbers of the form 3i, 3 times I, where I is 0, 1, and so on. What is the equivalence class of 1? Notice that 1 is not in the equivalence class of 0. 1 is not equivalent to 0. What is the equivalence class of 1? It's 1 and all the numbers that when you divide by 3, the remainder is 1. So it's 1 and 4 and 7 and 10 and so on. Or more formally or symbolically, it is all the numbers of the form 3i plus 1 for I equals 0, 1, and so on. Now we have the number 2 that's in neither of these two equivalence classes. Okay, let's look at its equivalence class. It's 2 and all the numbers whose remainder when divided by 3 is 2. So it's 2 and 5 and 8 and 11 and so on. And this is 3i plus 2 for I equals 0, 1, and so on. Now, what about 3? Well, I don't need to define an equivalence class for 3 because 3 is already in the equivalence class of 0. 4 is already in the equivalence class of 1, and so on. So if you look at this, every natural number is in one of these, in exactly one of these 3 equivalence classes. Now, one word I want to say about this notation here of 0 with square bracket. I chose 0 as the representative for that equivalence class, but I could have chosen any other element in that set as the representative. So for example, I could have said that this is the same as the equivalence class of 9. Okay, this is the same as the equivalence class of 301. Okay, but usually we choose one of those smallest elements or the more natural ones as representative of those. So if you look at these 3 sets, these 3 equivalence classes, one thing that you will notice immediately, or maybe not immediately, but if you think about it for a few seconds, look at these 3 sets and take their union. Okay, so take this 0 and 1 and 2. What do you get? If you take the union of these 3 sets, you will notice that what you get back is the set n. Furthermore, notice that no 2 sets share any element. So the sets are pairwise disjoint. So the equivalence class of 0 and equivalence class of 1 share no element. Equivalence class of 1 and equivalence class of 2 share no element. The same thing for equivalence class of 0 and equivalence class of 2. So we have this property that these equivalence classes, the equivalence classes of an equivalence relation, if I take the union of all of them, I get back the set A on which the relation was defined. If I look at any 2 of them, they share no elements in common. This is what we call a partition. Okay, so we say that the equivalence classes of the relation partition the set A. What is a partition? Partition is a mathematical term that if you give me a set A partition of A, for example, is a set of sets, A1, 2, 3, and so on, such that none of them is empty, no 2 of them share any element, and the union of all of them give me back A. So if I take this set A, so this is set A here, what is a diagram of its partition or Venn diagram? So this, I can partition it, I can divide it into subsets like this: A1, A2, A3, A4, A5, A6, A7. Okay, so if you look at them, A1, A2 have nothing to do with each other, no elements in common. A2, A3, no elements in common, and so on. If you look at the union of all these A1, A2 through A7, it gives me back the set A. None of them is empty. So these sets A1 through A7 are a partition of the set A. Sometimes there's one special case when we're talking about two sets partitioning a set A, we call that a bipartition. Okay, so if I look at set A and I look at A1, A2, I say that A1 and A2 bipartition the set A. Okay, but partition is a mathematical term where we divide a set into non-overlapping subsets, but where the union of all these subsets gives us back the set itself. Knowing this term now, partition, and understanding what an equivalence class is, we have a very important theorem about equivalence relations, which is that the equivalence classes of an equivalence relation defined on set A form a partition of that set. I remind you that for this relation R that we defined AB, A is equivalent to B mod 3, and the set was the natural numbers. And we looked at, there were three equivalence classes of 0, 1, 2, 3, 0, and 1, and 2. If you look at the set N, it's really partitioned by these three equivalence classes, 0, 1, and 2. Every natural number is in at least one of these three. No two of these equivalence classes share any elements. If you take the union of all three of them, then you get back the set of all natural numbers. So when we have an equivalence relation, the equivalence relation induces or defines a partition of the set itself. And this is one actually of the powerful uses or notions of the equivalence relation, because if you think about n, the natural numbers, it's an infinite set. It's an infinite set, but when we talk about this relation of equivalence mod 3, we really have now shrunk that set, broke it completely down into three elements. We are saying that under this relation of equivalence mod 3, all the natural numbers are really, there are three of them, 0, 1, and 2. Every other number is equivalent to one of those. And this is the fundamental theorem of equivalence relations.